When an immediate-release tablet enters a turbulent glass flask, or a patient's stomach, it disintegrates rapidly. The active ingredient floods the system all at once. Controlling that sudden release is a difficult challenge in pharmaceutical engineering. Getting the terminology wrong during this process has severe consequences. Every year, agencies like the EMA and FDA reject comprehensive dossier submissions because development teams misaligned their modified release claims with the actual formulation. The core problem lies in the baseline behavior of conventional immediate-release dosage forms. They create sharp, aggressive peak-trough fluctuations in a patient's bloodstream, risking toxicity at the peak and a loss of efficacy at the trough. This graph maps that exact problem. We see an immediate-release plasma curve generating a sharp peak, known as Cmax, and then a rapid drop. Overlaid here is the horizontal therapeutic window. The overarching objective of any modified-release formulation is to alter the drug's input rate, flattening that curve to keep the plasma concentration safely within this horizontal band throughout the dosing interval. To describe products that achieve this, the industry relies heavily on the term extended release, but using this as a generic marketing catch-all obscures the actual mechanics at play. That extended release umbrella actually contains two distinctly different pharmacokinetic objectives: sustained release and prolonged release. Their engineering intents are separate. Sustained release demands high-precision, zero-order architectures that push out drug at a constant rate. Prolonged release relies on lower-intensity, first-order mechanisms that simply slow the drug down. Conflating these two distinct frameworks in a target product profile guarantees a misalignment. If the physical tablet behaves one way, but the regulatory bioequivalence criteria demand another, the submission will fail. To understand why these submissions fail, we need to look at the precise mathematical targets required by each system, starting with prolonged release. This chart displays a typical prolonged release pharmacokinetic curve against our immediate release baseline. Notice the slower rise, the lower Cmax, and the extended tail stretching out above the minimum effective concentration line. The arched shape of this curve indicates it is utilizing first-order-like release kinetics. The concentration rises and falls smoothly, but it is not constant. A prolonged release profile explicitly accepts these moderate peak-trough fluctuations. The mathematical priority here is simply keeping the drug clinically active for a longer duration than a standard pill. That acceptable fluctuation is where prolonged release diverges from the stringent mathematical target of sustained release. Compare the arched PR curve to this sustained release profile. The SR curve achieves a flattened plateau. It maintains a near steady-state plasma level, approximating a rate in equal to rate out input over the dosing interval. Look closely at the trough concentration, or C-tau, at the end of the SR interval. It sits demonstrably higher than the immediate release trough, providing continuous therapeutic coverage. Regulators formalize the requirement for this steady plateau through a specific metric called the fluctuation index. It is calculated by subtracting the minimum concentration from the maximum concentration, divided by the average concentration. Regulatory agencies mandate that products claiming sustained release explicitly prove a demonstrably lower fluctuation index compared to the immediate release baseline. Prolonged release claims, however, are exempt from this strict metric. They only need to prove adequate exposure duration above the minimum effective concentration. Submitting a prolonged release style first-order curve under a sustained release regulatory claim is a mathematical trap. The fluctuation will be too high, immediately triggering a dossier rejection under SUPAC-MR guidelines. Achieving these distinct mathematical curves requires distinctly different approaches to physical matrix formulation. Here is the relatively unstructured physical breakdown of a prolonged release matrix. The tablet degrades and melts gradually over time in gastric fluids. Because prolonged release targets that arched profile rather than strict zero-order control, formulation scientists are free to employ simpler, lower-intensity release mechanisms. The strategy often involves blending slower dissolving excipients with moderate polymer concentrations. This delays the tablet's dissolution, but does not tightly control it. Alternatively, manufacturers use wax-based or fat-based matrices. These are designed to gradually melt at human body temperature, eliminating the need for highly sophisticated, expensive membrane coatings. Scientists will also strategically exclude super disintegrants, relying instead on modified disintegrants that inherently slow down the tablet's structural breakdown. These simpler physical mechanisms naturally yield the gradual, arched first-order release that perfectly matches the prolonged-release pharmacokinetic target. By prioritizing cost-effective, prolonged duration over strict precision flatness, this matrix engineering accurately fulfills its clinical intent without over-engineering the dosage form. When the clinical goal demands zero-order flatness, the physical engineering must shift to high-precision control. Sustained-release tablets face a hostile environment. They must resist highly variable gastrointestinal conditions, including shifting pH levels and the physical perturbations of food digestion, to maintain a perfectly constant release rate. This diagram illustrates a primary solution, the hydrophilic matrix, typically using polymers like HPMC. Upon contact with fluids, the outer boundary undergoes an initial hydration process, swelling into a thick, viscous gel layer. This protective barrier initiates a precise two-way diffusion process. Water molecules diffuse inward through the gel, dissolving the drug, while the active pharmaceutical particles diffuse outward at a strictly constant, uniform rate. The control lever here is the exact viscosity grade of the HPMC polymer. That grade dictates the thickness of the gel layer, which directly controls the diffusion path length the drug must travel. Some highly sensitive drugs cannot achieve the required zero-order flatness with matrices alone. In these cases, engineers deploy advanced systems, specifically the osmotic pump, or OROS. This architecture visualizes an osmotic pump. Notice the rigid, semi-permeable membrane enclosing the core, punctuated by a single laser-drilled orifice. As fluid enters through the semi-permeable membrane, it expands an internal push layer. This creates internal osmotic pressure, acting like a microscopic piston that forces the drug out of the orifice at a perfectly steady rate. Crucially, this osmotic delivery mechanism is entirely independent of the surrounding gastrointestinal pH. Whether in the highly acidic stomach or the neutral intestine, the release rate remains constant. Regulators demand this level of precision for a reason. Sustained-release formulations are often required to demonstrate a level A in vitro in vivo correlation. This point-to-point relationship between lab dissolution and human absorption is the rigorous standard expected for post-approval biowaivers. The strict mathematical flatness required by the sustained-release curve justifies this complex, highly calibrated manufacturing infrastructure. With the engineering mechanisms defined, the decision to develop a sustained versus prolonged release product cannot be driven by marketing aspirations. The formulation target must be dictated by the active pharmaceutical ingredients intrinsic biopharmaceuticals. Look at this decision matrix. The choice hinges on two key variables: the API's half-life and its therapeutic window. A sustained release architecture is mandatory for APIs with short half-lives of 2 to 6 hours, combined with narrow therapeutic windows where any fluctuation is dangerous. Clinical indications like hypertension or epilepsy treatments fall strictly into this category, as peak-driven toxicity or trough-driven breakthrough seizures represent major clinical risks. Conversely, prolonged release is the ideal choice for APIs with moderate half-lives of 4 to 12 hours, possessing wider therapeutic windows. Treatments for musculoskeletal pain are perfect candidates here. Minor concentration fluctuations are medically acceptable, and the primary goal is simply extending patient convenience to once-a-day dosing. Failing to evaluate these variables at project initiation leads to internal misalignment. If R&D formulates a PR convenience product, but regulatory affairs writes a dossier claiming SR steady-state control, the project will fail in review. True pharmaceutical innovation relies on scientific alignment. It means precisely matching the physical capabilities of your polymer matrix to the mathematical realities of your target pharmacokinetic curve.